Alright, College Algebra, we are now in section 3.2. We're going to be learning about how to do synthetic division and then using them in a couple of ways by evaluating polynomial functions using the remainder theorem and then testing for potential zeros. So let's go ahead and get started. Here's what synthetic division is. A synthetic division, it provides an efficient process for dividing a polynomial by a binomial of the form x minus k. This x minus k right here, you may hear me call it linear factor or something like that because that is what it is a linear factor. We can divide polynomials by anything of the form that has mx plus b in it. Okay? So, and I will show you a few examples of those. So let's go ahead and see this example. But before we get to that example, one thing we do need to remember about synthetic division is that to avoid errors in our division process, we must use zeros as the coefficients for any missing terms. So, for example, if I have the polynomial, let me see, if I have the polynomial x squared plus 2, and I want to divide it by x minus 1, well, this polynomial right here is missing that term of x. So how we would write it in our synthetic division is, or how we would see it as in our synthetic division is this right here. Like that. So any missing term, like this right here, we need to fill in with a 0, and then whatever your missing term is, x or x squared, or something like that. Okay? In this example, what we're going to do is use synthetic division to divide these two polynomials. And how I'm going to tell you to start is always take your denominator, take this denominator, set it equal to 0, and solve for that x, which is x equals 3. That is going to go on the outside of our synthetic division setup. And then what goes on the inside are the coefficients of all of our terms here. So 4, let me get my pointer, 4, negative 15, 11, and 10. And notice this polynomial is not missing any terms. It goes down from a power of 3 to 1, then none. So there's nothing missing. And we just need to take those coefficients, write them in this spot here, and here, there, and lastly, there. And now, first thing after putting it all together is you bring down the first number, and then you take that number, multiply it by 3, so 3 times 4, and it goes here. That's 12. Now, add together these two and drop it down and put in this spot here. So add together, we get negative 3. Now again, do multiplication. 3 times negative 3, place it right here. And 11 minus 9 is what you get there is 2. And again, multiplication. 3 times 2 and place it here, which gives us 6. And this last number that you get is known as the remainder. And I always place it in a little box to remind myself about that. And get 4. So we get the remainder of 4. Now to rewrite our polynomial after dividing it, these numbers right here are our coefficients on our new polynomial. So let's write it. We're going to get 4x, and it's always going to be one less degree than what you started out with. So 2 minus 3x, and then again We're going to go in stair-step order, like 2, then 1, none, okay? And then plus 2. And then we're going to tag on our remainder, which is going to be plus, then our negative 4 over our factor. Well, I circled the wrong one. It's going to be the x minus 3. So whatever we're dividing it by up here is what we're going to put our remainder over in our solution, if we have a remainder. So there you go. There's our solution after dividing those two polynomials. Here's something called the remainder theorem. If a polynomial f of x is divided by an x minus k, the remainder is equal to f of k. So we're going to be using our synthetic division to help us in evaluating what f of k is equal to. So I'll show you an example of that. Here we go. We're trying to evaluate what is f of 4. Well, normally, what we do is this right here. We say, well, f of 4, f of 4 is equal to, now replace all of your values of x with the number 4. So we go in and replace everything with 4. And then after we're done with that, we evaluate and get our solution that we're looking for, which is 17. I'm going to write that down. Okay, now using synthetic division, we can do the same thing, but our last number, the remainder, is going to end up being our solution, 17. So let's go ahead and do that. Now remember, 4 here is known as our 0. That's what we're going to put on the outside of our synthetic division setup. And bring down all of the coefficients, so negative 3, 15. We're missing our x squared term, so we're going to put in a 0 for it, and then negative 50 and 25. So negative 3, 15, 0, negative 50, and 25. And do your synthetic division process. So bring down the first number, multiply, add together, so 15 and negative 12. Then multiply 4 and 3, you get 12 again. And then add together, and then 4 times 12. And then we add together those, negative 2. And then multiply 4 times negative 2, get negative 8. 25 minus 8, 17. There you go. So the remainder is also the solution for this right here. You can get it 2 different ways. But if I ask you to use this remainder theorem to find a certain value, you better use synthetic division, not this up here. Okay, so here's another thing that synthetic division is really good for, is for testing zeros of a polynomial function. And how we're going to do that is set up our synthetic division and go through the steps of that. And if our remainder is 0, that's great. That means that number right there that you used in your synthetic division is a 0. If our remainder is something else other than 0, then that number is not a 0 to our polynomial. Okay? Okay, this example, we are asked to decide whether a number that we're given is a 0. And this right here, this right here is our potential 0 that we're trying to figure out whether it is or not. we're going to use on the outside of our setup of synthetic division. Then we're going to bring down all of our coefficients to -3, and we're missing our x squared term, so place that with a 0, -18. Now, bring down the first number, multiply 2 and 2, get 4, add together, -3 and 4, we get 1, multiply 2 and 1 to get 2 here, add together, multiply 2 times 2, get 4, and then we do get a remainder of -14. Since our remainder was not 0, that means k equals 2 is not a 0 of f of x. Okay, so there we go. Let's do another one. So we have another function f of x, and given another possible 0, so let's use our synthetic division to test whether that is a 0 or not. I'm going to bring down all my coefficients. 1, -4, -14, 36. Good, we're not missing any terms in this one. Okay, now bring down the 1, multiply the -3 and 1 to get -3, and we get -7. -3 times -7 is a positive 21. And then add together those, we get positive 7. Then we get a -21 when we multiply -3 and 7. And then we add together those to get, 15. -3 times 15 is a -45. And we do get 0 here. So k equals -3 is a 0 of our function. Okay, this is the last example that I have for you, and last slide I have on here. So, and it's also the most complicated because of this right here. We have a value of k, or potential 0, that is a complex imaginary number. And we can still use our synthetic division to do the division process and test whether or not this is a 0, but it's just a bit more complicated. So pay attention here. Okay, put your potential 0 on the outside, just like before. Bring all of your coefficients down. Okay, now drop down your 1, multiply together 1 plus 3i to 1. That's not so bad right now. So it's 1 plus 3i. So we get -1 plus 1 minus 3i. That's just going to give us 3i. Now we need to multiply together the 1 plus 3i and 3i together. So if you want, do this off to the side like this to get your answer that goes in this spot right here. And that is going to give us, let's see, -9 plus 3i. And then put together the 6 and the -9 plus 3i, get -3i, well no, we don't get -3i, we get -3 plus 3i. Again, off to the side, multiply together the 1 plus 3i and the -3 plus 3i. You're going to have to FOIL that together, and remember, I squared is the same thing as -1. And now, this right here, we get in this spot, -12 minus 6i. Put together the real numbers, we get 2 minus 6i. Now again, take your 1 plus 3i, multiply it to 2 minus 6i, and FOIL that. Put together all your like terms, and you will get 20. Which makes this a real zero, or a complex zero, of our number, or of our function f of x. So this right here, 1 plus 3i, is a 0, because our remainder ended up being 0. And that's all I have for you, so I'll see you all in class. Goodbye, everybody.